Today we're making cakes to test the validity of Newton's law of cooling. So baking a cake can be kind of boring to watch. So you know what's even more boring than watching us bake a cake? Watching it rise. So here's some jokes.
Why did the students eat their homework?
Why?
Because their teacher said it was a piece of cake. Why did the cake go to the doctor?
Why?
Because it was feeling crummy. What kind of cake do people in heaven eat at birthday parties?
I don't know.
Angel food cake. What's a dwarf's favorite kind of cake?
What?
Why, shortcake, of course. When the little boy was making a cake, why did he run away?
You guys!
Why?
Because the directions said, crack 2 eggs and beat it.
Alright, so we're going to take the cake out of the oven now and we're going to get some temperatures at various times. First, we're going to start off with time equal to 0, which is 80.3 degrees Celsius. We're going to get the temperature at time equal to 10 minutes, which is 62.2 degrees Celsius. And the last after 30 minutes is 56.8 degrees Celsius. And now it's time to do some math.
Newton's law of cooling is a law of exponential growth and decay given by his differential equation dt equals k times t of the object minus t of the surroundings, where the big T is temperature, and in this case we're going to be using degrees Celsius for our problem. So when solved for its equation integrated, t of t equals t of the surroundings plus t of the object minus t of the surroundings times e to the kt. Our temperature of the surroundings is 25.0 degrees Celsius, so we're going to plug those into the TS's up there, and our initial temperature of the object taken at 3:37 p.m. was 80.3 degrees Celsius, object being the cake. Now we want to solve for that K, so 10 minutes later, at 3:47, we took another temperature. So T of 10 equals 62.2 degrees Celsius. We plug in 10 minutes for the T up there, and then we're going to begin to simplify. So subtracting 25 from both sides, 55.3 e to the 10k equals 37.2. Then we divide both sides by 55.3, and then take the natural log of both sides. You get 10k equals ln of 37.2 over 55.3. Simplify for k, and you're going to get negative 0.03965. Now you can plug that all the way back up here in for k there, and you're going to get t of t equals 25.0 plus 55.3 e to the negative 0.03965 t, which will give you your temperature in degrees Celsius for any time t minutes after 3:37 p.m. Let's say there's a time 30 minutes from our initial measurement that we want to estimate what the temperature of the cake is going to be. All we have to do is plug in 30 minutes for the little t's right there and up there, and we just have to simplify it. So simplifying for t of 30, 25.0 plus 55.3 e to the negative 1.18939 equals 41.833. That number up there came from this times 30. Now, our actual temperature measured this time was 56.8 degrees Celsius. So there's something that's going on here and why our estimate is not more accurate. Basically what happened is that we left the cake on top of the oven, so that kept the cake warmer than it should have been by Newton's law of cooling. And so we also went ahead and estimated the error. With our predicted temperature as the standard, it comes out to 35.776% error, or if you use our measured temperature as the standard,
Alright, so what we've decided to do is that with any extra cake will be used at the discretion of the person that we pull from this hat. Alright. So the first choice would be Manu.
I gotta zoom in.
If for some reason he's absent, go to Christian G. go ahead and pick one last final person. And we'll go to Connor. If for some reason all of these people are absent, which I doubt Connor would be because this is our video, it will be at the discretion of Mr. Toshlock.